Now let's see an example of this very familiar signal once again through Fourier transform. So if you want to compute the Fourier transform of the rectangular signal, remember we started out with a rectangular wave which was periodic and then kept extending the period. Now what if a rectangular signal is given to us, okay, and it is told that the signal is non-zero for some duration t naught and for everywhere else it is 0. So this is the rectangular function for which we have to compute the Fourier transform. This is clearly aperiodic, so we cannot use Fourier series expansion. Let's try and compute its Fourier transform. So how do we compute the Fourier transform? We know that x of j omega is now integral x of t e power minus j omega t dt. The only thing now changes from the Fourier series analysis is instead of minus t by 2 to plus t by 2, you just go from minus infinity to infinity. That's all, nothing else. And of course, this 1 by t appears in the inverse Fourier transform. So that has just shifted place. So how do we evaluate this? So this is equal to 1 for minus t naught by 2 to plus t naught by 2, 0 everywhere else. So this gives us e power minus j omega t divided by minus j omega minus t naught by plus t naught by 2 to minus t naught by 2, which is equal to e power j omega t naught by 2 minus e power j omega t naught by 2 divided by j into 2 by omega. So what is this? This is sine omega naught t. This gives us 2 sine omega naught t divided by omega. So now this is the Fourier transform of this rectangular function. So earlier we saw that for a periodic rectangular signal where the period extended from minus t by 4 to t by 4 where it was non-zero and then the entire period was t, we got sine k pi by 2 by k pi as the Fourier series coefficient. So they look very similar, right? So that's because this is a very general class of function called the Sinc function that appears to be the Fourier transform of any rectangular signal. So we'll define the Sinc function as Sinc of any theta is sine theta divided by theta. Some people define this as sine pi theta by pi theta. Both turn out to be the same with the scaling factor, of course. So we can say that this is the definition of the Sinc function. We'll stick to this definition, that is sine pi theta divided by sine pi theta. So if we plot this Sinc function, let's say theta is equal to 0, then we get sine pi by sine pi 0 by 0, 0 by 0 form, apply L'Hopital, you get 1. So if you plot Sinc theta, this is what you get when theta is equal to 1. So when theta is equal to 1, you get sine pi divided by pi, sine pi is 0, so you get 0. So this is the first 0 crossing of the Sinc function. And for all integral multiples of pi, you get sine equal to 0. So here, whenever theta is equal to 1, 2, 3, all integers, you get 0. And for every value in between, you get positive or negative number. So this is how the Sinc function looks like. Sinc theta looks like this, where it takes 0 for all integer values of theta, and for every other values in between, it will be something which is negative or positive, where it alternates. Okay, and it is symmetric about the line origin, and that is true because, as you can clearly see, this is an even function, right? So you have a symmetric, which is an even function here. Sinc theta is a symmetric signal, okay, and there are 0 crossings at every integer values of theta. So if I have to, instead of theta, I can say that this is sinc of t and this axis is t, then this becomes a regular signal and it has 0 crossings for every integer values of t, and this is an even signal. Okay. So this is a very standard signal that we will come across often, because rectangular signal is a very standard signal which we would encounter in real life. And if we want to compute it Fourier transform, the frequency components that are present in it, then we'll have to know about this sinc function. Okay. So the Fourier transform of the rectangular signal is this sinc function. So let's represent the spectrum of the rectangular pulse using the sinc function. So if we represent that using the sinc function, then what do we have? We have to just multiply and divide by t naught. So you have t naught here and t naught here, and this we can bring that 2 here. So we have omega t naught sine omega naught by 2. So we are missing this pi, so you can say that you can replace this omega with 2 pi divided by t into t naught by 2 pi. Simplifying this, you get pi t naught by t, and in the denominator you get the same thing, which is pi t naught by t, which is nothing but t naught times sinc of t naught divided by t. Okay, or in other words, you can say that this is equal to sinc of t naught into omega divided by 2 pi. Okay, so this is in fact nothing but sinc of t naught into omega by 2 pi. So this is the representation of the rectangular pulse in terms of its spectrum. So this is the spectrum of the rectangular. So this is the spectrum of the rectangular pulse. Now it of course looks like the sinc we just derived. Now what is the amplitude at omega equal to 0? So we can just simply substitute that here. When omega is equal to 0, what do we have? We have sine 0 by 0 form. So all we have to do is just take the L'Hopital. If you take the L'Hopital here, you can clearly say that this is going to cancel out with this, and the only thing that we have is t naught. So the amplitude here is t naught. So that you can directly observe from here, right? So we are just simply scaling the sinc function with t naught. So here 1 has to get scaled with t naught, and that's what we are seeing here. And when is this first 0 crossing? The first 0 crossing is at 1 for the sinc function. So when is the first 0 crossing here? So this first 0 crossing will happen when t naught times omega by 2 pi is equal to 1. So when does that happen? For what value of omega does that happen? That happens for omega equals 2 pi by t naught. Okay, and so this value is 2 pi by t naught. And when is the next 0 crossing? The next 0 crossing is at 2. So the corresponding value of omega is 4 pi by t naught. So 0 crossings happen at integer values. So the corresponding value of omega is k 2 pi by t naught. This is 4 pi by t naught. This is 6 pi by t naught. And of course, this is a symmetric function. For that reason, we have 2 pi by t naught here, minus 4 pi by t naught, and minus 6 pi by t naught, and so on. So this is the spectrum of the rectangular pulse, and we know exactly where there is a 0 crossing, and we know exactly what is the amplitude, everything just by computing this Fourier transform. So one interesting thing to note here is, what is the bandwidth of this signal? What is the spectrum telling you about the bandwidth of this? Clearly the bandwidth of this signal is infinity, because the sinc function never goes to 0, never dies down. It has 0 crossings, but it never completely becomes 0. It goes arbitrarily close to 0, but never becomes 0. So for this reason, even though the rectangular pulse is a short, finite duration time domain signal, its frequency representation, the amount of frequency components it contains, is infinitely many. and that's what is denoted here through its bandwidth. So it has infinite bandwidth, even though the signal in time domain has a very short duration. Now, what about the other way around? So what if we want to compute the time domain representation of something which is finite in bandwidth? Let's say like an ideal low pass filter. It had a representation which looked like this, right? Something from minus omega naught by 2 to plus omega naught by 2. If we had a rectangular pulse in the frequency domain, that is, we had only a fixed set of frequencies to be added, then what would be the corresponding time domain signal that it would produce? Let's see that. So essentially we are trying to compute something of this form. So we are saying the spectrum now looks like this. So it is minus omega naught by 2 to plus some omega naught by 2. So this is the spectrum of some signal. If this is the spectrum of some signal, what is the corresponding time domain signal? So I want to compute that. And how do I compute that? Through inverse Fourier transform. So we used Fourier transform to compute the spectrum. Now somebody gave me the spectrum. From this I want to find the time domain signal. We said that the solution is through inverse Fourier transform. So what is the inverse Fourier transform? It is 1 by 2 pi integral minus infinity to infinity the spectrum just multiplied with the phasor as such, and now the integration is over the frequency. So you are going to add all phasors, right? So it is over all frequency. So what is this? This is 1 by 2 pi. Of course, this is 1 only between omega naught by 2 to omega naught by 2. Have e power j omega naught t by 2 minus e power j omega naught t by 2j to 1 by pi. Alright, and this is equal to, so this is clearly equal to sine omega naught t by 2. So we have sine omega naught t by 2 divided by pi t. So if we want to represent this in the Sinc term, what do we have? So we have sine omega naught pi t divided by 2 pi, and here we have, and we are supposed to get the same thing even here. To get the same thing, we need to multiply and divide by the remaining terms. So we have added omega naught, so the corresponding omega naught is here. We have divided by 2 pi, so the corresponding division is also here. So what would we get? So we get omega naught by 2 pi times Sinc omega naught t by 2 pi, right? So this is of the form Sinc of pi theta divided by pi theta. So we have exactly the same thing here. Okay. So in other words, something which has a finite bandwidth in its spectrum has infinite duration in the time domain. So once again, this is a Sinc function which is going to extend from minus infinity to plus infinity in the time domain. So what we understand from this is that whenever there is a finite length signal, okay, rectangular pulse is finite in length. So anything that has a finite length in time domain will have infinite bandwidth, and anything that has a finite bandwidth, like the rectangular representation in the frequency domain will have an infinite time length. We will see this more clearly when we study the properties of the Fourier transform. This is called the uncertainty principle. Anything that is bounded in time will have infinite frequencies and hence the bandwidth will be infinite. Anything which has a finite bandwidth will have infinite time length in its time domain representation. Both are the same signal. Once again, I am repeating this, only the representation is different, the signals are exactly the same. If you represent the same signal in the time domain, if it is finite, the same signal's representation in the frequency domain will require infinite bandwidth. And the same signal, if it has finite bandwidth in the frequency domain, the same signal in time domain will have infinite length present